Good afternoon. My name is Okoro of the Department of Process Engineering, Stellenbosch University. In this presentation, I will be discussing the comparative assessment of alternative fuel production pathways for sustainable road freight transport. We are all probably aware of the environmental challenges of unwanted emissions associated with long-distance freight transport. These environmental challenges are consequences of natural resource depletion global warming, which arise from the utilization of fossil-based transportation fuels. In an attempt to circumvent these challenges, the utilization of carbon-neutral fuels has been identified as a viable approach to satisfy freight transport's energy needs. The current study therefore explores the utilization of critical and sustainable feedstock for the provision and production of transportation fuels of ethanol, butanol, and the hydrocarbons of diesel, gasoline, jet fuels, and liquefied natural gas. Now, during the course of this presentation, the background and motivation of the study will be discussed. The methods employed in the study will be discussed, results discussed, as well as conclusions and recommendations from the study presented. As stated briefly earlier on, freight transport over long distances has been recognized as being a major contributor to greenhouse gas emissions, which leads to unfavorable environmental outcomes. The present study is particularly interested in land freight transport, since land transport accounts for about 77% of all freight, while road freight accounts for about 74% of total land freight income. Now, the dominance, the network is highlighted or illustrated using figure 2, as presented by agbizgrain.co.uk. You can see that figure 2 shows a highly distributed network of road transport systems. Now, due to the dominance of road freight in South Africa, opportunities clearly exist to reduce unfavorable environmental outcomes by the production of renewable transportation fuels. The renewable transportation fuels may then be utilized directly, either by blending these fuels with fossil-based petrol and diesel, or by utilizing these fuels as intermediate products, which can be further upgraded into higher value fuels such as jet fuels. Now, in this study, triticale has been selected as the preferred biomass resource for the production of renewable transportation fuels, largely due to its ability to be grown on marginal lands. So there's no possibility of competing with agricultural food crops for agricultural land. Furthermore, triticale is characterized by high starch content. It's a resilient crop that presents with high yield relative to a low input requirement. Now, I think most importantly, we have a significant amount of these marginal lands in South Africa. As an illustration of this abundance, we have quoted a Green Cape study that showed that we have over 100,000 hectares available within the Western Cape alone. Now, apart from the obvious advantages of utilizing biofuels to reduce said aforementioned emissions, the domestic generation of such biofuels will improve national security due to the reduced dependence on energy imports. Now, during the course of this study, we have compared, using a minimum fuel energy price as a comparative metrics, the biochemical and the thermocatalytic pathways for the production of the products of ethanol, butanol, and hydrocarbons. Okay, so here we have designated the biochemical pathways for ethanol and butanol production as case A and B, and the thermocatalytic pathways for the production of hydrocarbons and butanol as case C and D. All pathways in this study have been simulated using Aspen Plus as the preferred simulation tool. Figure 4 presented here highlights the production of ethanol from triticale. Now, figure 4 shows that triticale is initially grounded finely, then mixed with water such that a solid loading concentration of about 30 weight percent is maintained. The mix is hydrolyzed under the action of an amylase enzyme, with the hydrolysis mix fermented under the action of yeast. In this simulation, we have ensured that starch to glucose and glucose to ethanol conversions of 98 and 95% respectively is maintained, such that the overall yield of ethanol is about 0.47 grams per gram of feed. Now, the products from the fermentation reactor, the ethanol product from the fermentation reactor is concentrated using stepwise distillation columns to produce ethanol with a concentration of about 91% weight fraction, and with further concentration to produce anhydrous ethanol achieved using molecular sieves. In this study, we have considered utilizing the bottoms from the beer column as in the production of DDG, that is dry distilled grains with solubles. Now, these dry distilled grains with solubles are produced via multi-stage concentrator, right, to reduce the moisture content to about 10 to 12%. Right, these DDGs can be employed as a cheap animal feed. Figure 5 presented here shows the biochemical butanol production process using triticales as the feedstock. Now, utilizing the methods described earlier on, triticale is hydrolyzed and homogenized such that the hydrolyzed liquor is fermented under the action of a microbe of BA101 strand of the Clostridium species to produce acetone, butanol, and ethanol. Fermentation is enhanced via in situ AB recovery using CO2 gas stripping, thus reducing the possibility of inhibitory effects of the microbes present in the fermentation reactor. Cooling of the recovered vapor stream facilitates a condensation of a liquid product containing the target ABE products, such that further recovery of this ABE product is achieved via liquid-liquid extraction using 2-ethyl-1-hexanol as the extractant. Recovery of these extractants is achieved using a distillation column, while stepwise distillation columns are utilized in the recovery or the separation of the products of acetone, ethanol, and butanol. Now, in this particular study, the thermocatalytic production process for the production of hydrocarbons employs the ethanol produced from case A, presented earlier on in figure 4, right? So the ethanol produced from case A is used as a feed to produce the hydrocarbons. Now, initially, the ethanol is dehydrated to produce ethylene, right? With the ethylene purified to remove possible contaminants. To produce possible contaminants. Now, this ethylene is oligomerized to produce olefins. The olefins produced typically contain carbons C4 to C20, right? The olefinic mixture is then subject to a hydrogenation reaction to produce paraffins. Now, the paraffins are now distilled to produce the required or the target fractions of diesel, jet fuel, gasoline, and LPGs. Now, to ensure that the processes are self-sufficient, the high energy requirements for the oligomerization reaction that is about, because it occurs at about 120 degrees at a pressure of 35 bar, is satisfied using a portion of the LPGs to generate to satisfy on-site energy requirements. Of course, also ensure that we do not need to buy in hydrogen. Steam reforming is employed to produce hydrogen gas that is employed in the hydrogenation reaction. Now, the thermocatalytic butanol production process also employs the ethanol produced from figure 4 described earlier above. So this process here shows that the ethanol is subjected to a so-called carbon-carbon coupling reaction. This reaction is also called the Goubert reaction. The reaction is achieved under the action of a hydroxypipette catalyst at a temperature of about 298 degrees Celsius. Now, light volatiles are removed from the product mix using a flash tank, with further removal of any water contents achieved using molecular sieves. In this figure 7 also shows that the butanol is then recovered using a distillation column, right, with unreacted ethanol using another distillation column. Now this unreacted ethanol is recycled back in the system to enhance the butanol yield. Now, having simulated and modeled and simulated these processes, classic chemical engineering economic design approaches are employed to calculate the capital and the operating costs. Now, figure 8 shows that there is a gradual increase of this. There's an increase, obviously, in the complexity of the systems increase. The capex also increases. Notably, cases that are characterized by high temperatures, such as the thermocatalytic processes of case C and D, present higher capital costs. This may be explained by the need to utilize higher quality equipment fabricated using temperature resistant stainless steel. Now, further assessments of these processes using the minimum fuel energy prices shows that the most desirable case in this our study is actually case A, because it facilitates the lowest cost of energy, around $19 per gigajoule, with the least favorable being case B, which is the biochemical butanol production process, characterized by a high minimum fuel energy price of about 27 US dollars per gigajoules. Right. Now, we expect that over time we are going to be able to comparatively compare, and this is an ongoing study actually. We are trying to compare virtually all feedstock that exists within the South African space, right? Freely available sugarcane bagasse, invasive alien plants, garden waste, wood chips. We are going to compare their performances for the production of similar transportation fuels, right? So we can determine which of this feedstock is best, not just economically, but also environmentally. So at some point, a full environmental performance of these different feedstocks will also be assessed. Now, although in this particular study, jet fuels have been specified as the third most favorable pathway, right? There's, however, a potential for the jet fuel production process to be much more favorable due to the possibility of carbon taxes. We tend to create a premium price for biofuels. In other words, such carbon taxes will make the production of those fuels more economically advantageous. Thank you.